Okie dokie, chemists, let's get started. I wanted to show you this page. Is this thing working? Yeah. Okay. I just posted the new, final exam resources page. I put it on the top of the lecture modules just to super clearly show you that this is all the study material you have. There's some information about the final exam on this page. It's right here at the very, very top. See that? Oh, that's the Zoom session. So links to all the appropriate forms, like if you have a conflict with the final exam, you shouldn't have a conflict because we're using the university sponsored time period, so there should be no other final exam conflicts there. But if you do have some type of conflict, there's the makeup policy. Do know that with the final exam, and this is different, if you are to miss the final exam, there is a 15% penalty. So for midterms, we waived the penalty, but for the final exam, because we need to get those final grades in as soon as possible, we will have a penalty. So please show up to the final exam. Also, if you are an SLDS student, the 3-day window is not in place for the final exam. You must schedule your appointment with SLDS on the day of your final. So that's an SLDS policy, not ours, so do be aware of that. All right, so there's all the information. Here is the scratch paper that you'll receive, so it's already on there. We are going to add a couple more equations. The problem is we already have them printed, so you will get those additional equations, and I have those written here, what you will get, like Avogadro's number, Pivnert for some reason, they're going to give you that. So you'll have those. Do test your Respondus Lockdown browser again, so that's all there. And then down here are all of the different resources. So the department has not posted their practice final yet, but they will. They plan to this week, and that will be a Carmen exam. I have one packet posted already, so that's already here. It has 70 something questions on it. It's not a practice final, it's just 70 questions that are cumulative. I have another packet in the works. I just haven't finished it yet. It's over 100 questions and I'm losing my mind. I will post that later this week. So there's plenty for you to work on already. So don't, I wanted to provide this information as soon as possible so you can get started. And then I have all the older study materials as well. So chapters 1 through 9, you can use midterms 1 through 3 to help you study for those chapters. So there are all the practice exams. There are my practice exams, my previous Zoom sessions, and all my overview sheets. You ever write the same word over and over and over again, and it doesn't seem like a word anymore? That's how I feel about the word key. It's not a word anymore because of how many times I've written it. And the recitation packet. So it's all right there for you on that page. There is no reason for you to not or put off studying for the final exam, which is in about 2 weeks. Is that what it's about 2 weeks? Okay. All right. Any questions about the final? Any questions? Okay, so let's move on to finishing chapter 11. We may or may not finish today, if not, definitely on Friday. So that means we'll probably have 2 homework assignments due this Sunday, but do know that 11 and 12 is really short, just so you know. All right, so we left off talking about intermolecular forces. These are attractions between separate molecules. There's criteria we look at when determining, the importance of different intermolecular forces. For London dispersion, that weakest attraction, we typically look at molar mass or surface area. It's most important for nonpolar compounds. Then once we have polar compounds, usually dipole-dipole attractions become more important and more dominant. That's a stronger intermolecular force. Dipole-dipole, you can think of them as just little permanent magnets now are more attracted to each other instead of temporary dipoles like you see in London dispersion. And now for our third important IMF we'll talk about is hydrogen bonding. Really, hydrogen bonding is a special case of dipole-dipole that is just unusually strong. And so hydrogen bonding, you're looking for a really electropositive hydrogen. That happens when hydrogen is attached to a very electronegative atom with lone pairs on it. So what my trick is, these are the types of groups you want to look for. Hydrogen attached to oxygen, hydrogen attached to nitrogen, or hydrogen attached to fluorine. And again, you need lone pairs on that electronegative atom. These are what you want to look for. These are functional groups that you look for in the molecule that you are inspecting. So if that group is present, then that substance can adopt hydrogen bonding. It will have stronger IMFs than just something with a permanent dipole. And so hydrogen bonding is super important in biological systems because that's what holds our DNA, our strands of like DNA together, is through hydrogen bonding, like all of those nucleic acids that, nucleotides that, line our DNA. There's a certain orientation of hydrogen bonding that kind of zips them together. And so hydrogen bonding, I said it's strong, but it's not as strong as a covalent bond, like a hydrogen-hydrogen bond or hydrogen-carbon bond that holds a molecule together, like actually builds the molecule. So here, I think I say it's about 5 to 15% the strength of a covalent bond. That's fairly strong, strong enough to keep the DNA together, but not so strong that it can't unzip the DNA in order to make RNA to do replication. So you kind of need that like midway Goldilocks region, something that's strong enough but not too strong that you can't break it and have that be reversible. So hydrogen bonding, super important in biological systems. Your bio people will tell you more about that. I just want us to understand the criteria we look for, right? So let's look at some examples. So let's consider these two isomers. Let's remember what isomer means. Does an isomer have the same, like if we have two substances that are isomers, do they share the same structure or composition? Composition, yeah. So these two molecules have the exact same composition, meaning they have the same formula. They will have the same molar mass, but what's different is their structure. So their connectivity is a little bit different. But if you take inventory of all the atoms, you'll see they have the exact same chemical formula. So if we look at these two substances and their accompanying boiling points, we see a big difference in boiling points. So just looking at those boiling points, which substance has more IMFs present? Propanol or ether? Propanol, yes. Higher boiling points means more IMFs are present. So let's just check that. Let's identify the IMFs present in the samples. Do they both have London dispersion forces? Yes, because they both have mass. And, the idea here is that since they both have the same molar mass, same composition, they actually have the same London dispersion because we're just looking at weight here because they have the same molar mass. Do they both have dipole-dipole? Can they do that? If you look at the structure closely, I give you a hint. What's this little arrow here? That's a dipole moment. So they both have dipole moments. So can they both dipole-dipole? Yes, they can, yes. And we see that the magnitude of those arrows are about the same, so we can say they're the same. All right, so what did we just talk about in the previous slide that we have not considered? Hydrogen bonding, yes. So which one can hydrogen bond? Propanol, yes, because it's right there, the hydrogen attached to the oxygen with the lone pair. So you might be thinking, well, ether has hydrogens on it, but those hydrogens are connected to what? Carbon. So ether cannot hydrogen bond because it doesn't have quite the right criteria. And that's like a common mistake is students think hydrogen bonding can happen with any hydrogen. No, it's those three different groups, those different criterias there. And so that is why propanol has the higher boiling point because it has our 3 IMFs and ether only has 2. All right, here's a tricky one. Which substance can participate in hydrogen bonding? NH3 or NH4+. If you just look at the formulas, you probably won't get it. What should we also draw? Lewis structures, crap. So hopefully you know what ammonia looks like already. Ammonia, nitrogen, 3 hydrogens on it, but what's missing? That lone pair, yeah. If you actually go through the 6 steps, you'll get that. I'm just being lazy. What about NH4? Does NH4 have lone pairs on it? No, it doesn't. Yeah, so if we just draw it, we see we have nitrogen with 4 bonds on it. All right, and it's an overall plus charge. So which one can participate in hydrogen bonding? Just ammonia. So if you kind of, take my criteria, right, where you say, oh, it's hydrogen attached to oxygen, nitrogen, or fluorine, but you forget the lone pair part, you might get this question wrong. You might think, oh, both of them can actually hydrogen bond, but ammonium cannot hydrogen bond because it has no lone pair, right? So that lone pair criteria is important for hydrogen bonding. But no fear, ammonium can participate in other kinds of IMFs, so it's not going to be left out here in the conversation. It just can't hydrogen bond. It can do other things. All right, so we feel good about that? Okay, great. Great, all right, this is a tricky one. Which picture correctly identifies the hydrogen bonding? The hydrogen bonding interactions in a mixture of water and H2 gas, I guess. So remember what water looks like in terms of its Lewis structure. It's bent, it has the oxygen has 2 lone pairs, and then we have hydrogen. It looks like that. All right, so which picture has it so the red lines are just depicting hydrogen bonds? This one's tricky. What do we think? See? I hear some A's too. I hear some A's, and that's common. A or C. Why is B? Why isn't B the right answer? Yes, it can't be B, so hopefully your mind just throws that one away right away. B is pointing to the covalent bonds. All right, those are not covalent. Those are not IMFs, right? Those are the bonds between the actual atoms. We're talking about in this chapter attractions between different molecules. Okay, so A and C, how are these different? All right, so A and C. What I think you should kind of focus on here is look at the red lines and see what hydrogen, what oxygen are being connected, and see if that matches the criteria for hydrogen bonding. So if we look, let's just look at like this bond right here, this one. Let's highlight it in, I don't know, green. This one, I'll just circle it right there. This oxygen, is it highly electronegative, that oxygen? Yes, it is. Yeah, because there's lone pairs on it. It's not drawn on it, but that water does have lone pairs on it. And what this red line is trying to say is that it's attracted to this hydrogen. Is this hydrogen highly electropositive? Remember our criteria. It's just a regular hydrogen, all right? It is not highly electropositive because look at what that hydrogen is attached to. It's attached to this other hydrogen atom. Because if we look at it, can diatomic hydrogen participate in hydrogen bonding? No, because that hydrogen is not electropositive, highly electropositive. It's not part of our criteria. But can the hydrogen in water participate in hydrogen bonding? Yes, it can, yes. So A is actually not correct in the reasoning, and it looks correct because it's pointing hydrogens to oxygens, but it's just pointing any old hydrogen to any old oxygen. But remember the criteria. So if we look at C, if we look closely at C and every interaction there, we can ask ourselves, okay, is that hydrogen very electropositive? Yes, it is, because it's attached to an oxygen, and then it's being attracted to that electronegative oxygen. So in all of these examples, the hydrogen that's part of the hydrogen bonding is highly electropositive. So it fits our criteria. A, it's just pointing to any old hydrogen. So we can't accept that one. Okay, good? Okay, so hopefully I tricked you, but like you learned from it, all right? Don't just pick any old hydrogen. It has to fit our criteria. All right, other things. Okay, so that is hydrogen bonding. That's our third strongest. So now we'll look at our strongest intermolecular force, and that is ion dipole interaction. So this one's kind of weird. It's a little bit different. In our first three intermolecular force categories here, we were looking at like pure samples where you look at the structure or the composition of a pure sample. We actually only see ion dipole interactions when we look at ionic compounds that are dissolved in water. So the idea is, do you remember in chapter 4 when we looked at the solubility table, right? And some ions were like really soluble in water, like sodium plus was really soluble, acetate was really soluble, but things like, you know, phosphates, sulfides, hydroxides, those were very insoluble in water. And so this actually has to do with the attractions that come from ion dipoles. So this interaction, the name tells you exactly what's involved in the attraction. We have an ion that's interacting with something with a dipole. So we need an ion, such as like a salt, some type of ionic substance like NaCl, barium chloride, like those different things. We need an ion interacting with something with a dipole, and the most common one is water. Water is a very, very polar solvent. It has a really large dipole moment there. And so this is why salts dissolve in water. So chloride here, when we dissolve NaCl, like if you take solid salts, essentially these water molecules can come in, make these really strong attractions to the separate ions, chloride and sodium. They can align their dipoles to make really, really strong attractions and separate basically the lattice energy of your sodium chloride. Because the idea is, let's kind of throw back to chapter 4. What type of electrolyte is NaCl? Strong, yes, because it's ionic. So let's think about it. As a strong electrolyte, what does that mean? It splits completely into ions. It splits completely into ions because the water molecules is what we say, we solvate those ions where we have free ions present. We have sodium plus and chloride minus present. So I think the tricky thing with ion dipole is, okay, when do we invoke this? We invoke ion dipole when we have a salt dissolved in a polar solvent, usually it's water. So like NaCl aqueous is when ion dipole is at play. So this is why salts dissolve in water, because one of my pet peeves from the bio people, all right, bio people, they say stuff like dissolves like. You ever hear that? Like dissolves like polar stuff, polar solvents dissolve polar molecules. That sounds right, right? Non-polar solvents dissolve non-polar compounds, right? That's what they say. But if you think about it, salt, NaCl, does salt dissolve in water? Yeah, like use your intuition, like yes, it dissolves in water. Does salt look anything like water? No, it doesn't. So that rule, that like axiom that we use breaks down when we're trying to dissolve things like ionic compounds. And the real true reason is because a new type of intermolecular force is at play, and that's ion dipole. So let's talk about this. So this is the actual interaction that's happening. We have a chloride anion, and we see the positive parts of the water are solvating around it. Essentially, they're associating their positive like butts on that negatively charged chloride. If we look at the sodium ion, it's positively charged, so the negative tail part of your water molecule is associating with that. So there's your attraction. Those dotted lines are your attractions. It's really strong enough to break the lattice energy of NaCl solid. So the trends for ion dipole is a little bit different, right? So remember our solubility table? Y'all remember that? Yeah, okay. So hopefully you know how to read it. Basically, these top anions, they're very soluble in water with some exceptions. The bottom ones here are very insoluble in water with some exceptions. So let's kind of think about this and look at the significance of ion dipole. Why are these substances really soluble in water? So let's look at these three compounds. Based upon the table, which of these compounds has the poorest solubility? Which one won't be soluble in water, probably? Which one? Can we read that? Here, let me just zoom in, I guess. Zoom in. There we go. Can you see it? Yes. Which one? The hydroxide? Wait, no, sorry, these three. Which one has the poorest solubility? All of them? Iron, yes, thank you, thank you. We all just tired? We all tired, okay. Yes, iron sulfide is the least soluble. Can you get that from the, hopefully you can get that from the table because we are going to assess that in 2 weeks. And so how we got that, we looked at the ions here. Nitrates and chlorides are under the soluble grouping, but the sulfide is under the insoluble grouping, and we see they're not exceptions. So iron sulfide is the least soluble in water. So let's review kind of chapter 8. Of these compounds, which one possesses the largest lattice energy? Yikes, you got to remember that. So lattice energy, what do we look at? Charges, yes. So which one has the largest lattice energy? Iron sulfide, yes, because if we look at the charges, we have +1, -1. So we have a +2 attracted to a -2, but then for iron sulfide, we have +2, -2. That attraction is much stronger. You just have like stronger magnets that are attracted. And then sodium nitrate, it's just +1, -1. So we see that iron sulfide has the strongest lattice energy. It has the highest attractions, keeping that solid together. So if you think about it, if we want to dissolve something, we need to break that lattice energy. So iron sulfide has a really strong lattice energy. So basically what I'm trying to say is that the ion dipole from water is not strong enough to break the lattice energy of iron sulfide. Versus if we compare calcium chloride and sodium nitrate, they have weaker lattice energies. Do those dissolve in water? Yes, because the ion dipole that's created when you add it to water is strong enough to break the lattice energy of those specific salts. Does that make sense? So like comparing it to chapter 4 ideas that, these tables, they don't just like pop out of nowhere. There are some implications and relevance to other chapters we talked about. So the idea of ion dipole balancing with lattice energy helps us predict whether things are soluble or not soluble. You'll talk more about that in Chem 1220, right, in chapter 13. All right. Okay, so there we go. Ion dipole. So we talked about all four different IMFs. So here's the summary, all right, of our 4 different IMFs. We have LDF, dipole-dipole, hydrogen bonding, and then ion dipole. I like to think of it in its own category, all right, because it's only involved with like salts dissolved in water, while the other 3, typically we look at pure samples, pure molecular samples. And then I have those trends here. LDF related to molar mass or surface area, most important in nonpolar compounds. We have dipole-dipole attractions. It's important to have permanent dipoles in your molecules, so you're looking for polar molecules. And then hydrogen bonding, our special case, where you have hydrogen attached to these really electronegative atoms. All right, so there you go. Just grab that. Okay, that's our summary of everything. So just grab it in the recording, because I'm gonna keep going. I'm gonna do examples. Yes, take your picture. Okay, there we go. It's literally everything we just went over. So. All right, oh, and here's another summary. This one's in your book. It's the same thing, and it kind of like says the same thing. Look, polar molecules, they have dispersion as well because it counts as matter. Polar molecules also have dipole-dipole and those ideas. I like this chart because it tells you the strength of these attractions. So I like that putting actual numbers within there. All right, so I actually wanted to do examples. So let's do examples. We might need to draw things. It might be important to draw things. So let's look at these different compounds and determine what IMFs exist in these. So drawing the Lewis structure might help. So let's draw water. Hopefully you know what it looks like already. All right, so the things you need to ask yourself are, for each of these compounds, is it polar? Can it hydrogen bond? And that will kind of get you most of the way there. So does water have dispersion? Yes, yeah, that's a trick question. Everything has dispersion. So I can just go ahead and circle dispersion for all of these. Yay, okay, very good. But when is dispersion the most important? Nonpolar compounds, because they won't have anything else. All right, does water have dipole-dipole? Yes, because for dipole-dipole, we look for things that are polar. All right, so water is polar if you look at its Lewis structure, look at its molecular geometry, put on your bond dipoles. I just, think babies and bodybuilders and you say, oh yeah, it's polar. That it's pulling in one direction. There's an overall dipole moment. All right, can it hydrogen bond? Yes. Can it ion dipole? The question you want to ask yourself is it ionic? No, it's not, so no ion dipole, yeah. Because in order to have ion dipole, you need something that's an ion and you need something that has a dipole. Water has a dipole, but is it an ion? No, it's not, so it cannot ion dipole. Great. All right, CF4. Do we know what shape that is? Tetrahedral. Yeah, it's just a carbon with like 4 bonds on it. All right. It has dispersion. Does it have dipole-dipole? No, because it's all fluorines are the same, so it's not going to have anything else either, right? Because all those fluorines cancel out because it is a non-polar compound, so we can just stop. Well, what about CH2F2? This molecule is also tetrahedral, but are all the sites equivalent? No, they're not. We have 2 hydrogens and we have 2 fluorines. So if I draw it this way, is CH2F2, is that non-polar or polar? Polar, yeah, so it has dispersion. Does it have dipole-dipole? Yes, it does. Does it have hydrogen bonding? No. It has a hydrogen, but does that hydrogen fit our criteria? No, it's attached to a carbon, and that's not oxygen, nitrogen, or fluorine. All right. All right, and then no ion dipole because there's no ion present. Okay. C3H8. Does anyone know what that is? Propane, yes. How do you know it's propane? Because 3 carbons. Yeah, so it's 3 carbons in a row and then a bunch of hydrogens. So a good question. Is it polar or non-polar? Non-polar, yeah. All hydrocarbons are non-polar. So the idea, like dissolves like, it works most of the time, right? So when we use water as a solvent to like wash our hands, that's good at removing polar things, ionic things, because the attractions are high. If you are working with something really greasy, all right, and you try to wash your hands with water, are your hands gonna get washed? No, it's not. No, it's not, because water is polar, grease is typically non-polar. So if you talk to like your grandparents or your parents, they might say, oh, if something's really greasy or sticky, just wash your hands with gasoline. All right, yeah, if you ask your parents, they probably did that. Wash their hands with gasoline because it contains a lot of hydrocarbons. It's non-polar, so it's more likely to strip that grease and crap. Soap works a little bit differently. It's actually through ion dipoles that it pulls things out, but actually a better, safer method is actually to use hand sanitizer to wash all of that greasy stuff off. Because hand sanitizer has some non-polar components to it, and it can take that grease off. So don't use gasoline. But if you ask your grandparents, they probably did that. They probably did that. Okay, because it's non-polar. Or the idea like other solvents, like mineral spirits. Mineral spirits can typically dissolve things that water can't, and it's because of difference in polarity there. All right, did we answer that one? Yes, we did. Okay. This molecule, we have an oxygen in the center, and instead of hydrogens, we just have carbon groups on it instead. We just have carbon groups instead. So it looks just like water, just carbon groups instead. So it has dispersion. Does this molecule have dipole-dipole? Yes, it does, because it looks just like water. Yes. Can it hydrogen bond? No, now it cannot, because now those hydrogens, they're still hydrogens, but they're not directly connected to the electronegative oxygen, so no. All right, and then no ion dipole. And now the last one, NaCl dissolved in water, has dispersion. It does not have dipole-dipole, because when we think about NaCl, we have a sodium plus and a chloride minus. Those are just straight up ions, not polar compounds, or not things with dipole moments. It's just straight up ions. So there's no hydrogen bonding either, but there is ion dipole. Ion coming from the NaCl part, dipole coming from the water part. How do I know that water is involved here in this last compound? It's aqueous, yeah, so we know water is floating around, all right? I told you the ion dipole one like doesn't fit in this idea. All right, you feel good? Feel good. And based upon all of these, the degree of how many IMFs are present can tell us something about the boiling point of that compound. Oh, yeah, like this one. Okay. Of these pairs, which one possesses the higher boiling point temperature? So what are we looking for? The one that has more IMFs. Okay, great. So let's look at the first one. Water and whatever that is. So you might want to think, okay, do they both have dispersion? Yes. Do they both have dipole-dipole? Yes, they're both polar. Water's polar, and this molecule, because that oxygen is bent actually, that's polar as well. So kind of what is the strongest IMF that we're looking for in these two substances? Hydrogen bonding. So let's see if there's a difference. In water, how many of those hydrogens can hydrogen bond? 2 of them, so it can a hydrogen bond twice. But in this is ethanol, based upon the structure, how many times can it hydrogen bond? Oh, I already said it. Or my hand said it. But my mouth didn't say it. Yes, only once. So based upon that, which one do you think has the higher boiling point temperature? Water, yes it does. Yes it does. Okay, next one. These 2 molecules. These double bond chlorine molecules. These are isomers. They have the exact same formula. Do they both have dispersion? Yes. What about dipole-dipole? Only one of them, yes. So if you recall from, I don't know, chapter 9, where we looked at polarity. So we can see, just think babies and bodybuilders. We have 2 chlorines pulling kind of in opposite directions from one another here. So our trans 1,2-dichloroethene is actually nonpolar because those chlorines cancel out. Versus, so I could draw those bond dipoles. So those 2 vectors do cancel out in 3 dimensions. Versus these 2 chlorines do not cancel out. So this molecule, cis 1,2-dichloroethene, is actually polar. So which one has the higher boiling point? Cis, yes, because one's polar, one's not. Great. All right, last one. Diatomic bromine or xenon? Higher boiling point temperature. So again, just go through all of them. Do they both have London dispersion? Yes. Do they have dipole-dipole? No. So back up and go to London dispersion. What do you look at to try to differentiate London dispersion? Mass, yeah. So bromine, it's diatomic, so you need to double it, is like, what is that, 160-ish? 160? All right, and then xenon is like 130? Yeah, something like that. So bromine is going to be the higher boiling point temperature. Also, bromine is what phase at room temperature? Liquid, versus xenon is a gas. Yeah, and so you can kind of use your intuition there as well. If something's a liquid, yes, that its boiling point temperature is higher, right? And so room temperature isn't enough energy to like get it into the gas phase. Good. Also, bromine has, so we look at molar mass for London dispersion. What's the other thing we look at? Surface area. Bromine also has more surface area as well when it's a diatomic. So kind of doubly, it has more IMFs present. All right. Do you feel good about that? Yes, okay. All right, so boiling point temperature is a great way to track IMFs. There are also other trends with IMFs. Remember, it's attractions between molecules. So one of the properties we'll look at is viscosity. Okay, viscosity is how slow something flows. All right, how slow something flows. So like water has fairly like low viscosity, it flows pretty fast, but something like honey, right? How slow it flows, has a very, very high viscosity. So the general trend for viscosity is that the more IMFs that are present, the slower or higher the viscosity is. I like to think of it, again, attractions, it's like the molecules are hugging one another. So if they're hugging one another, if you pour it out of like a container, they're just all like grabbing onto one another and they don't wanna separate from one another. That's how I like to think of it. Does that make sense? Yeah. So more IMFs, higher viscosity. All right. It moves slower. But you ever have like honey at the bottom of your like container and it won't come out? And you like try to like get it out. What do you do to try to get that honey out? You slam it. You do what? You give up. No, honey's expensive and I'm cheap. So what I do is I microwave it. Yeah. What? Yeah. Okay, yes. Okay, so microwaving peanut butter. What changes about the consistency of peanut butter when you microwave it? It becomes thinner. Yes, it becomes more liquidy. So how does the viscosity change? It decreases. Yeah, so heat is another way, or temperature is a way to change viscosity too. When you heat something up, all right, it becomes thinner, it flows faster. It flows faster. All right. And so if you think about it, you know, my hugging analogy still works. When you heat something up, you're giving those particles more energy, right? They're a little bit more bouncy. So they're not going to be like held on as tight to one another. So it'll thin itself out. All right. And again, I told you I'm cheap, right? So I changed my oil in my car myself. But I try not to do it in the winter because when the oil's really cold, it flows really slowly. Anyone ever change their own oil in their car? Okay, you do it in the winter. What do they say to do before you drain it? What do you do to the car before you drain your oil pan? You heat it up. How do you heat it up? You turn on the engine, right? You turn it on for 5 minutes to heat up the oil so it flows faster, all right? So you heat up that oil to make the viscosity lower so it flows faster. Okay, there we go. And so the idea of viscosity, you can look at different numbers here. SAE ratings tell us how viscous something is. So the higher number, SAE stands for Society of Automotive Engineers. So these SAE ratings are on the oil type of your car. It tells you how viscous it is. So like 0W15 or 5W20 or whatever, those numbers tell you about the viscosity of that oil. The different numbers are cold crank versus operating temperature viscosity. All right, so oftentimes if your vehicle doesn't start very well in the winter, what you might want to do, though I'm not a mechanic, is you take a lower viscosity oil. So basically your cold crank, it can crank easier in cold weather. But I'm not an engineer or a mechanic. Okay, so that's viscosity. Viscosity decreases with increasing temperature because you're giving it more kinetic energy. All right, so the other trend, not as fun, is surface tension. All right, so the idea is like water has a fairly high surface tension. Leaves and bugs and stuff float on water. So where surface tension comes from is the difference of, how do I want to say this, intermolecular forces at the surface of a sample versus the bulk of the sample. And so surface tension is this lack of upward force at the surface of a sample. And so the trend is the higher the IMFs present in your sample, typically the higher the surface tension of your sample. So I like to show this picture. I think it's the easiest. So if this is like a water sample and you were this water molecule, think about if you looked up and saw another water molecule and you were attracted to it, think about the net attractions all around you, 360 around you. There should be, if you're in the bulk, there should be a water molecule above you, below you, to the side. So when you think about that, look at all these vectors. Is there a net vector or do they all cancel? It all cancels, yes. So a molecule in the bulk will not have a net force kind of acting on it, all right? It's kind of, there's no force on it. But where it's different is at the surface. If we look here at the surface, Think about your water molecule attracted to other water molecules around you. You're attracted to the water molecule to your left, to your right, below you, but are you attracted to something above you? No, you're not, because there's no water at the top surface here. So if you add up all of those vectors, do you see the net direction of those arrows? Yeah, it's pointing downwards. That is what surface tension is that this net force pointing towards the bulk of your solution. And essentially, the more IMFs that are present in your sample, the larger that missing piece is, and the larger the surface tension that you'll have in your sample. All right, but viscosity is more fun to talk about. There we go. All right. Okay, so those are some trends with IMF. So let's keep going. All right, I want to talk about phase changes and hopefully get to my demo. I have 15 minutes. Hopefully I can get to my demo. All right, so we talked about boiling point and how that trends with IMFs. So let's specifically talk about these phase changes and kind of the energies required of them. Do memorize these different names for phase changes. Some of them are kind of obvious, you know, melting, freezing, vaporization. That's when you boil something, liquid to gas. But some of the other directions, like gas to liquid, which is condensation, we don't use that term as much every day. And then between solid and gas, do know these ones as well. To go straight from a solid to a gas is sublimation, and deposition is the opposite direction. So each of these phase changes have an energy requirement attached to them. Like I said, boiling point temperature relates to how much energy is required to separate those particles, so break all those IMFs. So these enthalpy changes, the energy requirements for these phase changes, also related to that. So for example, we use delta H of fusion to describe the energy requirements between liquid and gas. Oh no, not fusion, sorry. That's vaporization. Delta H of fusion is down here between liquid and solid. All right, and then we have delta H of sublimation between sublimation and deposition. So we use the same number, all right, for vaporization and condensation. What changes is the sign. All right, so if to vaporize a substance, if it takes 10 kilojoules of energy to turn a liquid to a gas, if we did the reverse reaction, it would be a negative 10 kilojoules of energy would be released. So it's all about signs again when thinking about the direction of these phase changes. All right, and so because enthalpy is a state function, you see here that the sublimation step enthalpy is equal to the sum of the vaporization and fusion steps, right? Because it doesn't matter to go from a solid to a gas if we pit stop at a liquid. So these two sums is equal to our sublimation enthalpy. All right, so let's look at some enthalpy numbers for water. All right, so this graph shows the heating requirements to turn something as easy as ice to a liquid to a gas. There are some things we've already talked about, and then some new aspects related to enthalpies of phase changes. So if we look at this graph at the beginning, at point A, we're starting with solid ice, or like H2O solid at 25 degrees Celsius, negative 25 degrees Celsius. So if we wanted to melt that ice, the first thing we would need to do is first heat up the ice to its melting point, then melt it. Once we melt it, now we have 0-degree liquid water. We could then heat that water up to 100 degrees. We already know how to calculate that. Once it's at 100 degrees Celsius, then we can go ahead and put more energy in to boil it. So what I want you to focus on right here in this slide are these blue lines. These blue lines, you already know how to calculate all of these lines. We use Q equals MCAT. The heat required to heat the solid ice, to heat the liquid water or the water vapor, we use Q equals MCAT, where Q is the heat required to heat some type of mass, some amount of mass of water, times its specific heat, times the delta T, its change in temperature that you want to you want to change. But the detail here is that, in chapter 5, we always talked about heating water. It's 4.184 grams per, or joules per gram degree Celsius, but the specific heat for heating gaseous water and solid water, they're slightly different. All right, so the energy requirements, it's not 4.18 for all of them. There are different numbers. But regardless, we always use Q equals MCAT for those steps. When we just heat solid water, when we just heat liquid water, when we just heat water vapor, we use Q equals MCAT. What we haven't talked about are these red lines. How do we turn a liquid to a gas? Here we need to use enthalpy of phase changes, where all of the energy we put into the sample, it's not going towards heating the sample anymore. It's already 100 degrees Celsius, right? If you're boiling water. So any additional energy you put into the sample is not going to heat the sample. It actually goes to boil it off, so to change its phase. And that's the next part. We already know how to do the blue lines. What we care about here are the red lines. All right, so here is the energy requirement to melt ice. It takes 6 kilojoules of energy to melt a 1 mole worth of ice, H2O, to turn it 1 mole of solid into a liquid. Or think about steam. It takes 40 kilojoules of energy to convert 1 mole of water into a mole of steam. Sorry, liquid water to a mole of gaseous steam here. So we see that there's different energy requirements. Note here I say the enthalpy of vaporization is always greater than the enthalpy of fusion. Why do we think that is? Think about what vaporization is. You're turning what into what? Liquid to gas. Fusion, you're turning what into what? A solid to a gas. So just think, or not gas, sorry, liquid. Just think about that. Think about, what are you breaking? IMFs, right? But when you go from a solid to a liquid, do you break all the IMFs? No, right? You're just breaking some of them. You're still in the condensed phase, so that's not going to take as much energy as turning something from a liquid to a gas. In those cases, you literally break everything, all right? So vaporization is always greater than fusion. So these are the red lines where we have phase changes occurring at their respective melting and boiling points. So let's do some calculations. Okay. I think this is the last time we take out our calculator for the year. So how much energy in kilojoules is required to melt 275 grams of solid ice at 0 degrees Celsius, so that's its melting point, into liquid water? So which value do we use? Fusion or vaporization? Fusion, yes, we use that one. All right, so do I just multiply 275 by 6? No, because it's per mole. So the first thing I want to do is convert 750 grams of that solid ice to moles. So what is it? Oh, I gave it 18 grams is 1 mole of water, and that's something like 15.26 moles of water that we are melting here. And so it's that mole number that I'm going to multiply by the enthalpy of fusion. So 1 mole, it requires 6.02 kilojoules of energy. And so there's my answer. Okay, so 15.26 times the 6 kilojoules gives us the amount of energy it requires to melt that amount of solid water. All right, so the idea here is, it's different than Q equals MCAT. We need to convert it to moles, and the unit of enthalpy of fusion or vaporization kind of tells us that. All right, so the next one, how much energy in kilojoules is required to turn that same amount of water, but this time it's at 15 degrees Celsius, completely into steam at 100 degrees Celsius. So let's think about it. Just use your intuition. You have a bunch of water, it's at 15 degrees, and you want to boil it. So what do you do first? You heat it up, but all of that heat goes where? What observation do you change when you start heating 15-degree water? It starts increasing its temperature, but then once it gets to 100 degrees, does it keep increasing its temperature? No, it stops. It stops at 100 degrees and it starts to boil. So here's the strategy. You need to calculate how much energy does it take to turn 15-degree water to 100-degree water. What equation do you use to do that? Q equals MCAT. Yes, we've already done that. Q equals MCAT. Then what about the next step? Now we have 100-degree water, but it's a liquid, and we want to turn that into 100-degree water that is a gas, steam. What equation or what value do we use to calculate that? Do we still use Q equals MCAT? No, we don't, because the temperature is not changing. In this case, we're using enthalpy of which one? Steam? There's no enthalpy of steam. It's enthalpy of vape. So it's this one. We're using the other one that we did use, yes, vape, right? So yeah, we just plug everything in. And so these are two separate steps that you just have to add up singly. So Q equals MCAT, let's do that. So the first step of heating, I think delta T is what? 85? All right, so Q of the heating part is 275 grams times 4.184 times 85 degrees Celsius. So that just heating step requires, and I'm just gonna divide all of this by 1,000 joules to get kilojoules. This is something like 97.8 joules, kilojoules, sorry, to heat that much water. All right, so in a separate step, we needed to do the enthalpy of vaporization. So do I just take 275 and multiply by 40? No, you need to use the mole amount. So thankfully, we already have the mole amount. It's 15.26 moles. But this time we multiply by the 40 number, so 40.7 kilojoules. And that equals something 621 kilojoules. And so if you add these two numbers together, you get the answer of how much total energy is required to heat the thing up, heat the water up, and then boil it to change the phase. So we need to do things in separate steps, all right? It's some amount of energy to heat the thing using specific heat, and then another amount of energy to actually rip all those IMFs apart. And that is enthalpy of vaporization. Okay. Okay, that's the last time we use math. Say bye, calculator. All right. Okay, so when does water boil? When you're in your kitchen, when does it boil? At 100 degrees, yes. When water boils, it turns from a liquid to a gas, yes. Okay, so are these children in danger? Are they in danger? They're on top of puddles, right? Puddles evaporate, don't they? Right? Puddles evaporate. When puddles evaporate, you're turning what into a what? A liquid to a gas. So rethink that answer. Are these children in danger? Are they in danger of being burned? You might be thinking that, right? But the idea of, yes, water turns from a liquid to a gas. When it boils, it's at 100 degrees. We need to introduce a new concept to explain evaporation. They are not in danger, all right? That these puddles are slowly going to evaporate, not because it's boiling, but because of vapor pressure. Some water molecules have enough energy to escape the liquid phase to become a gas. So in order here for a liquid to change into a gas, first, kinetic energy needs to be above the IMFs, keeping that sample together in the liquid phase. Secondly, those particles need to overcome any external pressures that are being exerted on it, such as atmospheric pressure. So both of those things need to be at play. So evaporation is explained by vapor pressure. So gases, and liquids actually have this distribution of kinetic energies within them. So like we know, when we add heat, when we raise the temperature of a sample, we raise the average kinetic energy of the sample. So what happens is when we raise the average kinetic energy of the sample, some of the particles have enough energy to escape the liquid phase. and become a gas. So any of these particles that are above this minimum temperature have enough energy to escape. And break free and become the gas phase. So this happens at all temperatures. So vapor pressure, here are the trends. As IMFs of your sample increases, vapor pressure actually decreases. As the temperature of your sample increases, vapor pressure also increases. So I know this sounds really weird. All right, so right before we go, I just want to have us check our intuition, because I say vapor pressure, vapor pressure, vapor pressure, and you have no idea what I'm saying. Vapor pressure, think of it this way. Things that are smelly have a high vapor pressure. If they smell bad, that means the gas particles are there to like enter your nose. So think about it. Based upon these observations, things that are smelly have high vapor pressures. What has a higher vapor pressure? Water or nail polish remover? Nail polish remover has the higher vapor pressure. Yes, acetone, all right? Because it's smelly. There's a lot of those gas particles escaping the liquid, entering your nose, so that's why it smells bad, all right? So nail polish remover has a higher vapor pressure at room temperature. All right, so based upon this, which one has more IMFs, water or acetone? No, stronger IMFs. Water, yeah, think about it this way. Higher IMFs, the particles are hugging one another. If they're hugging one another in the liquid phase, are they going to let any of their friends go to the gas phase? No, they're not. But if they have weak IMFs, will they let their friends go to the gas phase? Yes, they will. All right. So we'll come back to here on Friday, and I'll do my demo.